Here comes the recording. All right, folks, we're going to be looking at the chapter 6 topics tonight from our textbook. Here are the learning objectives for the chapter. See, there a lot about data, a lot about databases, and some other interesting topics. I'm going to jump right to slide 6, where the material begins. All right, so the first thing that we're going to look at here, and probably maybe the most important takeaway from this chapter, is talking about databases as a construct, and arguably one of the most important constructs inside of IT in general and the whole field. For people that are going into a data-related degree, databases will be one of those things that you're going to be interfacing with constantly. How many of you here have already taken the database course or are already taking it? I'll pause the video just for a second. All right, because that helps me to understand where your knowledge is about this. So, therefore I can kind of like move through some of this information a little bit faster, where if you were coming into this completely, fresh off the street, never having heard a darn thing about a database before, the other assumption is normally you would take the fundamentals of IT class before you would take this too, where we talk about databases as well. But I always ask that question because I never really know what skills people are coming in with, or if they did well in the database class or paid attention in fundamentals of IT. So we have all those issues. But some key terminology here, and we're going to kind of look at these a couple of different ways, but these are some of the key terms that we throw around. The database, which is all the files of a database system put together. A file, or sometimes what we refer to as a table. And then you'll see this like breakdown that they go through. But ultimately, it kind of really boils down to attributes and entities. And I want to talk about that conceptually because whenever we're building a piece of information about someone or something, it's often in the format of thinking about an entity, whether it's a person, place, or thing, and then qualities of that object. So whenever we're dealing with, let's say we're dealing with, a database about music, for example, like your music library or something, the entity becomes the recorded piece, and the attributes would then be maybe the style of music and the songs on there, et cetera, et cetera. But that is a really, to me, an essential concept, the entity attribute system. And that kind of from there extends outward, because it is whatever entities that we're dealing with logically that dictate the data that we're collecting on them. I mean, that's really kind of the crux of it. And so if I was to, for example, consider you an entity that I'm collecting data upon, what kind of data might I collect? I mean, there's all sorts, right? And all of those pieces of data that I might collect about you represent some attribute relative to you, whether it's your name, your age, social security number, your DNA information, whatever that is. Those are attributes related to you. And when you think of that also in terms of programming terminology and how that correlates, and how attributes are often given to objects in like object-oriented programming, objects are entities and have attributes. So it's really kind of an interesting correlation, because often those objects also correlate to database tables very often in programming. So you see like these threads in IT that kind of stretch through all the different topics. This little slide I think is a pretty cool one, and I used to kind of do like this whole little dog and pony show in MIS classes talking about this concept. Like, what are bits and bytes, first of all. And some people will say, well, that's how computers talk, right? That's like one thing that people think about. And that's not really true. Symbolically, yes. Electronically, no. Electronically, what happens with computers is they deliver two states of electronic pulse, a negative electronic pulse or a positive electronic pulse, which then equate to the bits. So a 0 might be a negative 5 volts. 1 would be a positive 5 volts. And when we start to get a series of signals put together, it takes only 8 pulses to dictate all the characters that are possible in the ASCII character set. So that's 256 possible characters just based on those bits. So every time we hit a key on the keyboard, we generate 8 electronic pulses. And then if you think about if you're typing really fast, how much that's grabbing. And it's taking those pulses and then converting it into the letter, and then it gets converted into other information. But they start here because they're trying to show that information builds up from the most fundamental of levels on a computer from that electronic pulse, the 1 or the 0, the 2 states of the binary number system, and how that is used to drive everything that we do technologically is pretty astounding to me. All right, when we do start to build information about entities, we start to think about little pieces of information. So if in this case, they're looking at kind of like a student database, and they're looking at a course field in a table, just one column of the table. And in this case, it's the course number. And that's one attribute of a course is the course number. And that goes into one column in a database table. When you take a collection of information and you put it together relative to an entity in a particular table, then we have what we call a record, or one row of that flat file. And all the information in that row is associated together. It all belongs to the same entity, and all of them are attributes of that entity. However it's broken down, the ID, the course number, the date, the grade, for example. When we start to make this, more than one dimension, and we start to go rows and columns, so we have multiple records, multiple entities being recorded into the same table, each with their own unique attributes. Then we build up what we call a table or a file in most systems. And then from there, we take files such as this, combine them with other related files that have related information, and that's what builds up a database. And the whole concept of a relational database is that these files or tables of information have links between them. Maybe the ID number from one links to the ID number of the other. And if you guys have learned your database stuff, which it sounds like you have, this whole concept of primary key and foreign key and tables that are joined, for example, to pull information. And so that terminology, I think, becomes pretty important when you start to look at it from that standpoint. Why do we have databases to begin with? Well, what did we do before we had databases? Well, that's a pretty simple answer. In most situations, we had paper, right? And so we'd write stuff down either in a ledger or on a piece of paper, and we'd put that paper into a folder. The folder would go into a file cabinet. Maybe there's some sort of hierarchy or organization, and hopefully the record was kept clearly. But there's a lot of problems with paper-based systems, and many times, when you think about this, have you ever been in a situation where you've gone somewhere and you filled out a form to do something, and then you get sent somewhere else and you have to fill out another form to do something? Government's really good for this, right? Or at least historically used to be, where you would just go over and over again, entering the same information over and over again into the same form, and how redundant that is. And one of the reasons why we moved away from these types of systems is because of some of the problems that you see here, right? People sometimes in different departments keep their own records. They have, maybe you're involved with an organization and one department knows that you changed your address and the other department doesn't. That kind of stuff happens all the time. Still, even with all the computers that we have, stuff is inconsistent. And really, when you start to think about paper-based systems, you walk into a doctor's office where, guess what? Most doctor's offices still are operating on paper. Right? And there's a comfort that comes with it. But how is it to just walk into a doctor's office, nobody's looking, you can pull the thing in and look on somebody's file, and there's no security on it at all. It's not like it's locked down. In fact, a lot of doctors' offices, they have those open, like, wall file systems, on paper. Interesting. All right. So when we start to think about, kind of like the traditional way that people would manage files in the past, and, even in this modern era, a lot of companies follow these techniques, by the way, is they have all these different departments that keep all their own data, all their own information, often redundant information, sometimes driving their own applications and their own databases, even if they're electronic. And I think it's just silly, when you think of it in that regard. But what happens is organizations do start small, And they may have started in a time when the technology wasn't around. And as it grows, think about what happens as it changes. You know, things develop discreetly, and then it's later that people realize that, oh, this would be good if we link these together, or if we put all the information in one place. Wouldn't that be a lot smarter? And sometimes it takes a while for that to happen. But the thing that really, at least in the modern business world, that brought it all together was what we call the database, which is that collection of related tables like we talked about. And then more importantly, the system that runs the database. And there's two concepts here. And I think a lot of times students have a misconception between these two constructs. The first construct is the structure of the data itself. So for example, the tables that are created with the information inside them, and then the links and the joins and the primary foreign keys and all those things that actually form the connection between the information. That's the database. However, that just sits there. It's a passive construct. It takes a database management system in order to be able to provide you a way to interact with the database, to give you ways to, pull information out or control access to it, or to link it together in ways that you might not even think about, all typically through the use of some sort of a query language or reporting tools or a combination of those things. Now, why do people put things into databases? Well, one of the reasons they put things into databases is databases, if one construct is holding all the information for an organization, it allows people at higher levels to kind of aggregate that data and look at it in different ways. So for example, here, we might have one large data store, then you have some sort of a database management system. Now, in the database class, what database management system are you guys using? Yeah, it's called
SSMS.
Right. Yeah, SQL Server Management Studio.
Very good.
Data Azure Studio.
Oh, that's right.
So Arnie, you're using Data Azure Studio?
Yes.
Or Azure Data Studio?
Yeah.
And see, that's actually a really good point, because you guys are taking this class, so you're like, oh, we're working with SQL Server. That's the database software tool. But the database itself are just files in that construct. It is SSMS that really allows you to interface with it. So that's the database management tool. But it's interesting that you guys are working with probably the same AdventureWorks database, but Arnie's using a different piece of software to access it, right? And that's what a database management system is. It sits on top. And in some cases, a lot of custom application development that you see within organizations are people creating interfaces that do all the database work in the background and then give you a friendly screen to look at, rather than having to learn how to write a SQL query or install SQL Server or run SSMS or any of that stuff. Normal users don't want to do that, right? So application developers create program interfaces to allow that to happen. It's a real big area of development, by the way. But the key takeaway here is that one DBMS, or it could be several, right, can create interfaces for different departments with different needs. And so if you're looking at somebody in HR, they have one person that just deals with benefits, and then you have another person that just deals with payroll. And these two probably shouldn't cross mingle. It doesn't matter to the benefits person how much this person is making or what their social security number is, probably, and vice versa. It's irrelevant information. It's specific to the task. They talk about this whole concept of the relationships and how those are formed, and knowing that you guys have studied a little bit of database helps a little bit, because some of this terminology won't be completely foreign to you. But they talk about key fields and how most database tables typically have to have some sort of a field that makes each record in that table unique. And usually we'll have one field that is that key field, and we typically will call it the primary key. So for example, a lot of database tables will just have one column that's ID number, and it might just be a record ID, and that might be the only unique piece of information. Otherwise, it might be something much more specific. So like if it's you going to school, for example, your unique identifier typically will be your student ID number, because although rare, it is possible that you get two individuals named exactly the same way, same first name, last name, middle name, born on the same day, hopefully not live on the same street, but weird things like that do happen, right? So that's why you have unique identifiers like the student ID number. Interestingly, when I was first going to school way back when in the Stone Age, we used to use our Social Security numbers as our student ID numbers at almost every school. In fact, the first 2 or 3 schools that I went to, they did that. And they would print it on, heck, they would print it on the envelope when they would send you your schedule. It was on the outside of the envelope. They didn't even think twice about it. And that changed. Before the 90s came to a close, schools started switching away from Social Security numbers. There was even a time, believe it or not, where you could hop out on the internet in the early 90s when the internet was like this new thing. You could go to the IRS website, type in somebody's Social Security number, and look up their whole pay history, just like that. Public record. The scary thing is you could also get their Social Security number too. So the IRS wasn't even in tune to that. All right, so they start to talk about these tables and how they relate together. But often when you're dealing with information, some of these tables, how do you link them together? And you guys probably learned this in your class in database. But you look at pieces of information that logically link together. So for example, here we have a table of suppliers with their supplier number. Here's their ID field, by the way, their primary key probably, the supplier name, address, etc. And then here you have a table that's keeping seemingly track of part numbers purchased or something, and who purchased them or who's supplying them, more likely. So it looks like this door latch, part number 137, which costs $22, comes from supplier 8259. And so what a relational database in essence does, folks, is it takes some pieces of information like the supplier number, which would be a foreign key here, links it to the primary key in this table so that we know that if we need to order more of door latch number 137, we get it from CBM Incorporated. And the relationship is really this connection between this field and this field. Here, the field is a primary key. In this table, it's a foreign key, right? And so if we're ordering parts, whoever we're ordering it from, they better be on our supplier list. Otherwise, we won't know how to contact them. So those are some of the operations that really, by this point in your database class, if you're taking it concurrently with this course, which many people are, some of the words or commands that you see here are ones that you probably have learned. Select is usually the first one that you learn, select from where, those types of clauses. And then joins are really big too. That's how we allow tables to connect to each other with a primary and foreign key relationship. So those, you learn about inner joins, outer joins, left inner join, right outer join, all those weird things. And by the way, those database skills, folks, I hear from so many people that go through these programs, those are some of the most employable skills that we teach in many ways, because databases are involved in so many things, and you can imagine how important that is in the data field. They're showing some other stuff, some more connections here, but really let's get down to this next slide here, where they're talking about how we're looking at the information and what capabilities really we have available to us in a DBMS. So the one thing that we have available to us is we have this ability to create what we call a data definition or a data dictionary, kind of combining those two things. So like when you are putting a table together, how do you let somebody else who's looking at it understand what is it you're putting in this table and why? I mean, why are we collecting this piece of information and not that piece of information? And why are we listing it like this? That type of thinking. So usually you have to think about this and define your database tables. The other thing that we have is learning this capability to query the database or extract or insert information or control it using the SQL language. And there's this whole argument, by the way, out there. If you guys, aren't aware of it in the IT world, with like old school IT people will often have this argument: is it SQL or SQL? Because they're both considered correct, and so it depends on who you talk to. So some people will say, well, it's SQL because it's an acronym, right? And there's other people, no, it's SQL because we decided a long time ago it was SQL, and you're a nerd for not knowing it, that kind of thing. And depending on what circle you travel in, people have arguments about it. I'm sure there's many Reddit subreddits or whatever about just that whole argument that go on forever. The other thing is that some of these DBMSs, and one thing that you probably have noticed is that SSMS is not one of them, has also the capability of creating beautiful looking reports. And if you want something like that, you usually use a separate reporting tool or a higher level product. And I don't mean higher level in terms of capability, but higher level in terms of like user accessibility. Microsoft Access is a little bit easier for creating reports. A lot of people will go to even third-party applications for creating reporting, and that's a real big thing. And part of what we're learning in Data Analytics 1, because I know all three of you are in that class, is doing basically reporting using Excel in a sense, where we're going to pull information from a database and start to convert it there. All right. When you start to look at a data dictionary, here's an example of one, and this is a snapshot from Access. And I always liked this feature about Access because whenever you were building tables, you could go in there and look at all the fields that you had in the table, the data type that it is, and then what kind of thing you're looking for, the description, and then you could go in here and just very granularly control it. Whereas if you learned how to write SQL statements, which is how you guys learn, right, you do this stuff all through code, right? So when you create it, it's all about the command that you type, and but there are graphical ways to work with this too. So if you're not a big fan of writing SQL statements, a lot of people sometimes will translate up the chain a little bit and use a graphical tool like Access to do some of the work. Access really isn't considered a professional level tool, but you can do some really powerful database stuff with it, and you can build full-blown applications with it as well. A lot of people aren't aware of that, but it is actually a pretty powerful product. But it seems to kind of be getting phased out in Microsoft Office, by the way. If you start looking at your Office installations that you're downloading these days, you'll notice that in many ways Access is not there, and they're migrating it to the cloud using this new thing called lists. So if you do it through Office 365, Access is now called lists, and I'm not really sure why. It has a little bit to do with SharePoint, kind of interesting in itself. All right, so as you guys have been learning your database stuff, you definitely have been learning how to do SQL statements, and here is just an example of what a SQL statement looks like. So I would hope, aside from the fact that you don't know what any of these tables or data are representing, this is the typical anatomy of a SQL statement. So you usually do select statements, you list what tables you're pulling from, what criteria you're looking for, and it's not quite like programming, which I hope you guys have figured out by now. It's really just a fancy way to evoke information to query the database. If you're working with a product like Access, and you notice here, if you look really carefully, you can write queries graphically. It'll show you your table connections graphically. And then you can just come in here and say, I want this part, I want this one to be included, that to be included, and for this one the criteria is, you just type it into a box. But what's really happening on the back end of all that, by the way, and this is kind of interesting, is that it is writing a SQL statement in the background to actually do the work. And Access, if you've ever used this product, allows you to actually switch into the code view so you can see the SQL statements. And I see some of you nodding that you've done this before. It's kind of interesting. So it's an interesting product to explore and work with. And in some cases, a lot of like introductory database instruction typically happens with Access. Those of you that are in the fundamentals of IT class, we're going to try to see if we can explore that a little bit. We're not going to get real deep into it during class, and we're certainly not going to do that here because I am counting on the fact that the database class is teaching you databases and that I don't have to. But we're talking about it from a higher level conception here. Some of the important things that database people learn, and I think that data people like us should be aware of, are some of these terminologies here. Some of these things are things that you will have to do for your database class. So the first thing that we talk about is this concept of conceptual design versus physical design, which is really funny because we are talking about virtual constructs, right? We're talking about a database, which is basically electrons somewhere, right? It's information. It's not something we can like physically touch, but we think about physical design. So conceptual design often is we just basically think about a problem and we think about the entities involved in that problem, the attributes that are relevant to solving our problem, how those attributes connect together. So we, in essence, can maybe just grab a piece of paper and maybe if I was thinking about like what sort of database I might want to build, let's say to store my music library information, right? I might start thinking about like, well, I got CDs, I got cassettes, I got, whatever. I got all these different genres, and am I going to alphabetize or whatever? You're just thinking about it. So in concept, you're starting to think about the information. Now, the physical design is when you actually get into the DBMS and start to actually build the tables, whether it's access or SQL statements inside of SQL Server Management Studio, whatever. When you're actually writing the SQL statement to build that table and run the query in it, you've built the database, you've built the table, I'm inserting information into it. That's the physical part of it. So the physical part is electronic, but conception always comes first, and planning is a big part of it, especially if you're working from scratch. Now, most of us typically professionally won't be in that situation unless you're a database administrator that's working on a project from a fundamental level. If you're an application developer, you might create databases to store and retrieve information. But for the most part, for us, it will be like, here's how you get to the database, here's how you log in, here's the table the stuff is in, there you go, there's your data. That's kind of what most data people will do. Some people will actually get kind of wrangled into the whole database area. So you might get pulled into a company where very few people know much about their databases, and if you know a little bit, hey, guess what? You might become the database person. But that's not a bad place to be in, and I'm going to tell you why, because those people are very, very valuable to companies, especially if that database drives operations in any way. So if like what you are functionally doing is controlled by that database, and you're the person that knows that database, you just wrote yourself job security, folks. So that's something to think about there. This next thing that we're going to look at over the next couple of slides, we're going to look at what we call normalization. We looked a little bit of referential integrity already, and then entity relationship diagrams. And I want to start first with this normalization thing, which just basically shows like if you are thinking about building a database and you're gathering information, a lot of times you don't really think about how you're going to break that information down logically so it fits well into tables that link together. And this is where some of the redundancy comes in. This is kind of like you go to one department and you fill out a form with your name, address, and phone number. Then you walk down the hall and you go to the other department and you got to give them your name, address, and phone number all over again. Makes no sense, right? When the real functional piece of information is something else. And unnormalized data is basically that, where you have all the information you need, but it's not really broken down logically. The process of normalization really is this: to break the data down into the parts that go together well. So maybe a supplier table just holds information about the supplier, and then the part maybe has the supplier information in it, but it really only holds the information about the part and maybe the cost. And then maybe these other tables kind of, I'm not sure how these relate, but all that stuff that was here is now broken down into tables that are smaller and more efficient. And therefore, every time I list a part number, I don't have to list the supplier address with it each time. That's what normalization is. Normalization is removing the redundant and unnecessary data from a database. And initially, the reason they did this was a functional one. And this is kind of interesting, I think. They originally did this because they worked on IT systems that were so primitive that any way that they could save memory or processing power by doing symbolic links to things. Why would we list a whole supplier address here? If I could just list it somewhere else and refer to it, then I could save every time I look at a record, retrieving all this information too. And that's going to make my application run faster because I got an Apple IIe with 64K of RAM, or whatever primitive device that you're using. And they used to think about that stuff real carefully. They used to be really particular about how many characters go into a field in a table. Because if we have twice as many as we need each time, we're chewing up all that disk space, and disk space used to be expensive. We used to think about it. So part of it came from functional IT needs, but then what ends up happening is this normalized data leads to much more powerful and efficient operating databases, even in an era where we don't think about processing speed and storage anymore. So I think that's pretty fascinating. So normalized data is a really big thing. Another thing that database people do a lot with a DBMS is they create what we call entity relationship diagrams, where they show this symbology. And I don't know, if you guys formerly were forced in your database class to learn what these little markings are. You had to do these diagrams and then draw in the symbols. I don't know if your teacher made you do that. Some people will allow you just to make the connections visually and just screenshot it. Some people have you draw it out. What did you guys learn?
We're doing it. We're drawing it. We're drawing it out and putting all the relationships.
I think I've only had to do one assignment with that.
Yeah. You usually don't spend a lot of time doing it, but how the data connects is important. So in some cases, really what an entity relationship diagram shows, for example, a supplier, for example, will only appear in the supplier table once, but it might appear in the part table many times because they might supply many things. So this format here indicates a one-to-many relationship. And people that are database designers know that. Now, in many cases, if you use tools like Access or SQL Server Management Studio, they have these little icons that are in there that show a 1 and an infinity. One to many is kind of how they do it. But that concept is pretty important for how databases function. Now, interestingly, relational database systems are the big thing. All right. And have been for a long time, and they're not going away, folks. That is kind of the granddaddy way to store data, and it's going to remain that. However, we are seeing this huge uptick right now in what we call non-relational databases, where we're putting things into basically data sets that are controlled by, I would think of it as a more flexible format is really kind of a better way to say it. The thing that is kind of interesting about that is because of the way the data is stored, which is not necessarily in unique tables. It's really individual records of information that can link together through other mechanisms. It has this beautiful ability to scale to really large systems really well. And this has become really interestingly heavily used by web developers. A lot of these, what we call NoSQL databases, because in many cases, they're really easy to create as a construct that you just attach to an application and it travels with it really easy, especially if the data that you're dealing with isn't huge. Now, if you are dealing with a huge set of data, now you have this different type of flexibility because we're kind of breaking some of the bonds that we would normally have through the relationships in database tables. And sometimes they're allowed to more freely traverse the information and extract search results. This is an area that's poised to grow, but I think it's pretty specialized right now. So it's really interesting to see where it goes. Does anybody know a named product that fits under NoSQL? Okay, one that we teach in the web program, if you ever take any of our web classes, is MongoDB. If you want to explore one, MongoDB is a really popular one. And you can read about NoSQL databases. It's pretty interesting how they work, actually. It's not too much different, but concepts are basically the same, ultimately. But the other thing that's really big that's happening right now is a lot of databases, and we heard this during our IT advisory board meeting too, is a lot of people are moving some things off premises, or things that used to be on-prem, as the IT people say, and moving it to the cloud. And in many cases, people that are starting out brand new in organizations, if you're building an organization from scratch, people are now, even big companies, are now thinking when they start, why should we have this big server infrastructure with all these people running it? We're just going to buy this service, hire a couple of people to run it, and our databases and our applications and are now being pushed up to the cloud. Who are the biggest cloud providers? Well, some of them are listed right here. Microsoft is huge, so Microsoft's Azure Cloud. Amazon Web Services is huge. And both of those platforms allow you to basically create containerized server environments that allow you to run just about any kind of application or database that you might want. Why do people put their stuff out in the cloud? Because it's secure, right? So we got Microsoft and Amazon looking after it. Now, from one of our articles from earlier where Microsoft got hacked, we weren't maybe always so confident that it's always secure, but in principle, it's more secure. You would think that their security is better than something you could run on your own network. It's also replicated and usually in multiple locations across the planet. So the other thing that comes with it is worldwide availability easily, that if any one data center is knocked out, that those data centers are replicated to other locations, and your data is really never going to get destroyed. So that's one reason people are doing it. But usually the biggest driver of moving to the cloud is the cost. And so, there's all different sorts of methodologies for doing this, by the way. There's companies you can pay. They give you like remote database services. A lot of people create what they call private clouds, which is basically they, put their databases out on the internet and have kind of their own way to access them. We do that here at Gateway quite often. In fact, that you could even think of like when we will be extracting data in the Data Analytics 1 class on Wednesday, you could think of that setup as a private cloud because it's really what it is. And you'll see that when we start to manipulate it. All right, let's move on to the next slide here. Now we start talking about this weird concept called big data. And that's a really fancy way to say, like, we have so much stuff that we can't fit it onto one server rack, one database platform. In fact, some companies get so complex with these things that they have multiple large database systems consuming huge amounts of space. I think that most of you have seen in the Data Analytics 1 class, we'll just pull in a CSV file with like 10,000 rows and how that makes Excel gag a little bit. And that's just 10,000 entries in one table. So what if you have like 10,000 tables and 10,000 databases and then extrapolate a huge amount of data and what that looks like and what is the big issue here? Why do we call it big data? Is because so many companies run that way. And then more importantly, we want to be able to extract data from all of those sources and analyze it all at the same time. That's some pretty heavy stuff. It requires some pretty specialized types of data constructs and software to kind of dig through that. So this is where we get to, kind of the BI part of it, the business intelligence aspect of it. And, they start to list a bunch of different tools here over the next few slides. So the first thing they talk about is a data warehouse. This is kind of interesting because it says a data warehouse stores current and historical data from many core operational transaction systems. All right, so if you think about a company that functionally does some sort of operation, whether it's manufacturing or service or healthcare or product distribution or whatever, and you have all these systems that constantly grab data. So like, let's say if you're at a company that is a wholesaler or a manufacturer, you're manufacturing product that goes into database, you're shipping product that goes into database, et cetera, et cetera. And then how do you aggregate those systems? So if the sales system keeps sales data, and then the salesmen who should earn the commission are in the HR system, and that's a different database. How do we combine these? So data warehouse is really a kind of collections of like weird data and conglomerations of weird, sometimes non-related systems, frankly. From there, we kind of move up to this uh, concept called the data mart. But notice that data marts have a little bit of a difference, and that is that they typically focus on a single aspect of a business. So it might just be accounting, or it might just be shipping, for example. One thing that has grown in popularity over the last decade or so is this technology called Hadoop. And this is kind of an interesting technology that maybe you've read about in some of your readings. But notice what it says: it enables distributed parallel processing of big data across inexpensive computers. Okay, so this is kind of a weird concept that came from the open source computing community a number of years back, where they used to take large problems or large sets of data that needed to be crunched, and rather than assign it to one like supercomputer or one computer that like, okay, that one's going to run that process for a couple of days and then we'll get an output at the end, they started to take large data sets and distribute them to multiple low power computers that would work in tandem. So in other words, they would take all their processing power and in parallel across multiple computer systems crunch through a large amount of data that would otherwise take the single computer system an exponentially long time to complete. And so they have specialized software that was created a number of years back that allows for parallel processing, and that's really what this is. The fascinating aspect of something like Hadoop, there's kind of like living, working examples of this out in the real world. One classic example, and where some of the technology came from, by the way, have you guys ever heard of the SETI project, the Search for Extraterrestrial Intelligence? In fact, it would be kind of interesting to kind of look that up. A number of years back, this was launched, and so this is actually really kind of fun. And no, thank you, of course. But basically, the point of this organization is they take radio telescope data from multiple observatories around the planet that are always on, scanning certain parts of the sky, reading the entire electromagnetic spectrum, and then dropping it into a file. And then, so we read the skies and we looked at all these electromagnetic frequencies. We put them all in a database, and now we've gathered so much data that we need. This one computer will take 1 million years to process the data, something ridiculous like that. And so what they came up with is a way to take the data, and in the old days, you'd come to this site and you could download the software and you'd load it up on a machine, and when you'd just like leave it on overnight, and while that machine was idling overnight, it would download data from SETI, process it, and send it back up. And the thought was, well, we don't have enough computing power to do this on our own, so why don't we send out the data to the worldwide computer of networks? Whoever wants to help us with this, let their computer system process the data and then send it back to us. And then we can see if we can find, ET sending us a message from the other side of the galaxy. And so far, they haven't come up with that, except for once, right? And you guys may have heard about this. And it was called the WOW signal. In fact, this happened back in the 70s, right? And it was part of the SETI project, Search for Extraterrestrial Intelligence. And they found a spike in the data. And it was so anomalous because you see, like, they're recording like little blips of frequencies with signal strengths, and 1, 2, 3, 4, 5, 6, those are all pretty normal. And when it gets up into the alpha characters, when it goes past 24 and it gets up into the letters, and it's like a strong signal. And it was so anomalous that they, in the printed out transcript, they wrote wow. So it's called the wow signal. So at one point they thought they found a signal. Interestingly, they have found some more recently, and they've decided that a lot of these were either pulsars or other naturally occurring space phenomenon. But they still keep looking, and this project is still going. But they very classically use this concept of parallel computing, which is what Hadoop is, to have multiple computers work on the same problem at the same time. Now, the problem with Hadoop is you have to really, in order to enable it, it's a pretty sophisticated setup, and I hope someday maybe I can like enable this on campus. It takes a specialized set of skills, and I'm working with our networking people, but basically to create these multiple servers that have a shared file system across multiple machines with different types of databases all working in tandem, and then sharing the workload of processing all the data from those across multiple machines. In fact, could be distributed as far as wide as you want it to be, really. SETI got really bold, and they asked the public to help them. And I thought that was fascinating, a fascinating approach. With the thinking is like, hey, if your computer finds that one signal, you could be famous too. That kind of thing. Almost as good as like buying your own star and naming it, something like that. All right. So finally, the last slide in this little sequence of 3 talks about what we call in-memory computing. And this is kind of a bizarre concept in itself, because normally we use a computer system. The software that we use is loaded up on the hard drive. That's what we call secondary or long-term storage on a computer. And when we run that program, we pull down the executable, we load it into RAM, and it runs from RAM. That's where a program runs from. And then you also, typically, if you're loading a data set, you can drop that into memory as well. And then when you're all done with your work, you save it, usually save the files back to the hard drive. But what they're talking about here with in-memory computing is where all of those processes, the active program that's running, where we pulled the program up from, and where we are storing the data are not being pushed to secondary storage, which is slow, by the way. They're doing what we call in-memory computing. So you get these computers that have huge amounts of RAM that are using portions of RAM as what we call RAM disks. And because of operating strictly in RAM, RAM operates at significantly faster speeds than even the fastest SSDs. We get super fast throughput on it. So it's like this really high-end way to do computing. It's a concept that's been around a long time and been used for a long time. It has a significant impact on processing speed. So if you have like a processing task that might take hours or days on a regular server, this might cut the time down significantly. There's some really interesting areas of computer hardware too, by the way, where companies are starting to use this technique. I was doing some laptop shopping over the weekend, and I noticed that HP has in some of their like obscure notebook models this thing called Optane memory. Have you guys ever heard of that? Yeah, it's interesting because they listed it as onboard RAM is how they listed it, right? So in other words, you have your regular RAM for your computer. So I was looking at this weird system that had 32 gigs of RAM and 32 gigs of Optane memory, which was kind of like a memory space. And this is what was kind of fascinating about this. It's a memory space that acts like RAM, has the speed of RAM, but when I turn off the computer, whatever's in that RAM does not go away, kind of like an SSD. And what ends up in that particular RAM are things that you do all the time. Your operating system, what are applications that you load constantly, whatever data you're using all the time, whatever data files, databases, things like that. And a lot of servers have been employing this technique for a while. And now we're starting to see it in personal computers too. So it's another layer of memory that sits independent of regular RAM and hard drive, but behaves like regular RAM. And this is a pretty exciting area of development for IT, I think. When we start to look at like how these more high level, data constructs work, and you look at this thing, they talk about data marts and data warehouses and clusters of databases, and the reality is that big organizations kind of use all of these things in combination. And you can count on the fact that the bigger an organization gets, the more they need to employ aspects of this or all of these different things to make it work. Hadoop clusters are kind of an interesting thing because I hear like varying information from people. Some people are moving away from clustering, and some people are moving towards it. A lot of the technologies that tend to drive that clustering software, by the way, are all open source, like Linux-based things, which is why a lot of big corporations tend to stay away from it just for that reason. But that's, I think, a really kind of interesting thing, using multiple low-powered computers to simulate one big one. When you start to look at some of the tools that we get to use in terms of actually digging into data, they have kind of a quick list here, and then more detail on the subsequent slides. The first thing that we want to talk about is this thing called OLAP, which stands for, as an acronym, not very intuitively, Online Analytical Processing, with on and line, I guess, being two separate words. But this concept of working with multi-dimensional data analysis, and this is kind of one that's a little bit weird, because when we think about number systems, we don't usually think in terms of dimensions. And so what do we really mean by that? What we're thinking about is how many variables we're dealing with in our equations typically. So when you're dealing with a couple, 2, 3 variables, you're dealing at a certain level, but sometimes you're adding aspects onto it that it's kind of like thinking of like the pivot tables in Excel, for example, where you're just taking the same information and shifting it different ways and looking at it different ways. When all that data is still there, it's just a matter of how you're looking at it. So that's one aspect of it. Actually, this graphic is, I think, pretty helpful, because if you were looking at maybe all these different products here, 3 different regions, maybe where they're being sold or produced or whatever, and they take the actual numbers that they actually created. Let's say this is a production chart. And then you can just simply add a dimension to it just by looking at projections of what you think it might be. And then add another dimension that might be a different projection or assumption, or flawed products or whatever. And every time you add another set of data to this that goes across all the regions and all the products, you're adding another dimension. So it's not really like you're working in 3-dimensional space, although the graphic kind of represents that. This is what we mean by multi-dimensional data. So we're looking at data that's interrelated, but a different attribute relative to it. And it does tend to form this like matrix, which is kind of interesting, I think, as well. Going back to the data mining thing, and this is one of those areas that kind of combines certain technologies, by the way. So like in one way, we can find this using some basic analytic tools. So we can, by charting and graphing, for example, or creating trend lines or whatever. In other cases, we have to write computer code using specific APIs in order to recognize certain patterns. But data mining is all about that. It's about finding patterns that we might be missing. And that's really kind of an interesting field, because you could look at information that's normal and then you get like that wow signal, that one anomalous piece of information. And that's the one that matters, is the one that one that's wrong is the right one, or that piece of information that holds the clue to solve whatever problem it is we're trying to solve. And so why do people do the data mining? So they do it basically for that. But it's all really about this, hidden patterns and relationships that you might not otherwise see intuitively. Some people have an eye for spotting things and some people don't. But in some cases, even people who are well tuned into the data might miss really, I think, pertinent features about it. So a couple of other interesting ones, and I find these kind of interesting. Text mining, where we are looking at this piece of, or type of software called sentiment analysis software. So what do you suppose that refers to? Sentiment analysis. That word.
Does it have to do with, like customer loyalty, that type of thing?
Sure, absolutely. How about like a movie review?
Yeah.
right? Like, I don't know if you guys are in the habit of doing that, but if you're watching like Netflix or Amazon or whatever, you might like, this show looks interesting. I'm going to read the reviews. Oh my God, the reviews are horrible. I'm not gonna, and some people go as far as actually searching, like they'll bring up the reviews and they'll search a word. This is sucks or awesome or best show ever, that kind of thing. And that's really what this is referring to. But a lot of it is really qualitative, is really what this is. So we can search word based and search for qualitative information. The other one that's kind of interesting is web mining, and this is something that you may have touched upon depending on who you took your Python class with. You may have done a little data scraping, or maybe you were given a link and you pull down data from a website. And then you take that data and you feed it into an application and create a graph or a chart or list it or whatever you do. But that's really huge. And so there's a lot of repositories online where you can maybe not necessarily go into a database, but the content on a web page was pulled from a database. And then you read a web page and write code, usually in Python, by the way, to look through that page and pull the pieces of information off the page that you want, and then use it to work with. And that's becoming a really big thing. So web mining is happening quite a bit now, and people have some pretty sophisticated engines for doing it. A lot of companies are putting stuff that is on their databases and making it web accessible. So Nick, perfect tie into the article. Actually, Dennis, you had that article with the police department, where here we are taking the misbehaving New York police officer database and putting it online for all to see. And that's the kind of thing that's been happening. What does it take to do that? What does it take to put a database online? Sometimes very little. A lot of our web servers already usually will have a database product running because a lot of web applications require it. In other cases, you can have databases that sit behind firewalls but still drive the content for a web-facing application. Now, there's a lot of pieces that you have to put in place to make that work. In some cases, you will have, for example, somebody sitting at their computer, they're going through the internet, they get to your web server, and then the website, you got all this information, but little does the user know, like behind that web server, you might be interfacing with an application. So even though you're pulling down a web page, which might be a single file, that's interfacing with an application on a different server, which is then pulling its data from a different server where the database resides. And, and maybe that's just running the DBMS or some specialized SQL queries, which is actually going to the actual file system where the information is stored. And so there's like all these like encapsulated layers. And this is really common, really, really common, especially in application development and web development, where we do separate these things. We'll have one server delivering the pages and the images and the styles, and another one dishing out the application that's pulling it from another machine, that's pulling the data from a different machine, et cetera, et cetera. That's very normal and interesting at the same time. Now, whatever organization you guys are going to work in, they're all going to develop their own policies for dealing with information. Now, if you are a organization such as the one that I work for, Gateway, we're a public institution, right? So we're an aspect of county and state government, technically. And a lot of the information that we have, some of it needs to be protected, some of it is public record. For example, like the financial information about how we operate is public record. The I think even my pay status is probably public record. You can probably look it up on a database somewhere. How much money does Ty make? I'm sure you can Google it. But when it comes to other types of information, I want you to think about this. Should it be public information how you paid your tuition? Whose business is that? Well, frankly, nobody's, right? Except for the people you owe the money to if you're borrowing it. But what about your other personal details? Well, we have very specific rules. For example, some of them are federal, some of them are internal, where we have policies that monitor how we share information. One I think that blows people's minds very often, and we've talked about that in this class before, is the fact that if I ever have a student who's not an adult, right, who is a minor, technically, if they're taking a college class, I don't have the right to share their information, like their grades, for example, with their parents. I'm not allowed to do that by policy. So we have this data governance at Gateway, and some, believe me, I haven't been one of the teachers that have taken the wrath of parents, but I've heard from others. It's like, what do you mean you can't tell me why my son is failing? It's like, they have to sign a waiver, sir, but they're only 16. That type of thing is a very real thing. So, what kind of policies an organization has is pretty important. So, some things are very, very tight. And in some cases, database administrators have access to really, really sensitive information that other people in the organization might not. So one of the reasons database people sometimes make a lot of money is because they do have access to that information, and they need to keep it private. How good is the information you're putting into that database? We talked about this, I think, way back when. If you're putting information into some sort of a repository, it's only as good as the accuracy of whatever you're putting in there. So if, like, you guys each give me, a not real date of birth and I put it into my database, well, my data quality is pretty crappy, right? So something to think about. All right, last slide, yay, that we're not even talking about. All right, so we're all done. We covered all the key topics in chapter 6, and I hope you guys can see how important I think this chapter is to what we do in this degree program. It's pretty huge, and I know that some of the concepts are really being dug into deeper depth with the database class. So we're not teaching you how to do tables and stuff here or write SQL code. But there's this assumption that you are learning this and that you understand it. And then more importantly, some of the bigger concepts, the big data, clustering, some of those concepts, data warehouses, data mining, and cloud computing, and all those constructs, those are ones that will be revisited continuously throughout your degree program and talked about pretty heavily. In some cases, we'll get to play with some of the technologies, and I think that's a lot of fun. All right, folks, that's going to end this lecture portion. So this lecture ends here.